Hello, hello everyone. Hello. Okay, everything is clear. So, hello everyone. Very good evening. So, welcome back to the 12th lecture of discrete mathematics, and we are discussing set theory and relation algebra. Okay. So, what happened in the last class? In the last class, we have discussed the concept of finite group. We just said that uh, if the underlying set of the group is a finite set, then the corresponding group will be called a finite group. Now, we just saw that finite group of real numbers with respect to addition is only the set containing element 0, which is the finite group of order 1. And with respect to multiplication, the only finite groups of real numbers are the set containing element 1 and the set containing element 1 and minus 1. Otherwise, the closure property will dissatisfy. So there are only three groups of real numbers with respect to addition and or multiplication. So we went further and we said that we can eventually create some more finite groups of imaginary numbers with respect to multiplication. So cube root of unity will form a finite group of order 3 with respect to multiplication. Fourth root of unity, that is 1 minus 1 iota and minus iota, will form a finite group of order 4 with respect to multiplication, and so on. So any set of n roots of unity will form a finite group of order n with respect to multiplication. But then we said that okay, so these are just the imaginary number. Can we have any other? Can we have some more finite groups of real numbers? So then we said that we may have some more finite groups of real numbers, but we will have to change the operation. We cannot use simple addition or simple multiplication. Otherwise, the closure property will not satisfy in a finite group and the set will eventually become infinite. So we said that we will modify the operations. So with respect to addition, the modified operation is addition modulo m. So we will divide the summation of a and b by m, and whatever the remainder is will be a addition modulo m b. Okay, so this one operation, we know that the result of the modulo m operation will be between 0 and m minus 1. Therefore the closure property will never produce a number because of closure property we will never have to include a number which is m or greater than m. Similarly, with respect to multiplication modulo m, we will never have to include the number in the set which is m or greater than m. So these are two new types of operations with respect to which we can define some more finite groups of real numbers, but with respect to addition modulo m and multiplication modulo m. So first of all, when we were having the class, then we had to face some power failure in between and we could not complete the topic, that is order of an element of the group. So we'll complete this first and then we will move to the today's topic, that is subgroup of a group. So this is what we are going to discuss. First, we will cover this concept of order of an element of the group, and then we'll discuss subgroup of group. Okay, so let's move further. So this is just the recap. This I said. Now let's have the recap first. Finite group, we just know that underlying set must be finite. These are just the definition. I just want to reach to the slide where we faced some technical issue. So let me just quickly. Okay. So this is your multiplication modulo m operation. This is your addition modulo m operation. That's what we have defined. A addition modulo m will be nothing but the remainder obtained by dividing a plus b by m. So if a plus b is less than m, then the remainder will be a plus b only. If a plus b is greater than m, then we will divide a plus b by m. Whatever is the remainder is, that will be the output of a addition modulo m with b. And similarly, a multiplication modulo m with b will be nothing but the remainder obtained on dividing ab by m. So if ab is already less than m, then the remainder will be nothing but ab only. If ab is greater than m, then we will divide ab by m. Whatever the remainder is, that will be the output of a at multiplication modulo m with element b. Okay, then what did we say? Sir, if we take any set from if we take the set of all integers from 0 to n minus 1, if we take the set of all integers from 0 to n minus 1, then it will form a group with respect to addition modulo and this from the last class. Now we know this set will be closed because if we take any two number and we divide it by n, the remainder will be between 0 and n minus 1. Therefore, we will not have to include any new number into the set. So it is closed. Addition is associative. Therefore, addition modulo m is also associative. The identity element with respect to addition modulo m will be nothing but 0. So it is present in the set. Therefore, identity element is also present. Apart from that, for any inverse of identity element will be identity element itself. Apart from that, for any element x belonging to set, what will be the inverse? Sir, x added with what, and such that if we divide that resulting number by n, then the remainder should be 0. So if x is added with n minus x, the result will be n, divided by n, result will be 0. That is the identity element. Therefore, for any element x, the inverse of x will be nothing but n minus x. Clear? So this is just one thing, and I just give you an example that if you take any set from 0 to n minus 1, let's take 0 up to 4, that means this 4 is nothing but 5 minus 1. So this is a set of all integers from 0 to 5 minus 1. Therefore, it will be a group with respect to addition modulo 5. Then we were discussing the concept of group with respect to multiplication modulo, and we had to face some issue. So let's look at this concept. So what is the logic? If n is any positive integer, if n is any positive integer, then set of all positive integers. If n is any positive integer, then set of all positive integers which are less than n and co-prime to n. The set of all positive integers which are less than n and co-prime to n. Co-prime means what? That the GCD of those two numbers must be equals to 1. The only common divisor of those two numbers should be 1. Then only those two numbers are called co-prime or relatively prime. So the set of all such numbers which are less than n and co-prime to n is guaranteed to form a group with respect to multiplication modulo n. With respect to multiplication modulo n. So we were taking an example, and let's start from here. So let n equals to 8. Let n equals to 8. Okay. So what are all the numbers which are less than 8 and co-prime to 8? Numbers are less than 8 co-prime 8 are, sir, what are the numbers? 1 is co-prime to 8. Yes, sir. 2 is not co-prime to 8 because the GCD of 2 and 8 will be 2. 3 is co-prime to 8. 5 is co-prime to 8. 7 is co-prime to 8. So these are the 4 numbers which are less than 8 and co-prime to 8. Therefore, we can simply say that the set containing all these numbers 1, 3, 5, 7 form a finite group of order 4. Form a finite group of order 4. 4 elements with respect to, sir, these numbers are co-prime to 8. Therefore, the operation will be multiplication modulo 8. Form a finite group of order 4 with respect to multiplication modulo 8. So let's try to understand this, that sir, if we take any two numbers from this two set, and if we perform the multiplication modulo 8 operation, then the result will also be present in the set, that is, it is closed. So please check. 1 into 1 divided by 8. 1 into 1 will be 1 divided by 8, remainder will be 1. 1 into 3 is 3 divided by 8, remainder will be 3. 1 into 5 is 5 divided by 8, remainder will be 5. 1 into 7 is 7 divided by 8, remainder will be 7. So we are done. So 3 and 1 we already checked. 3 3s are 9. 9 divided by 8, remainder will be 1. 3 5s are 15 divided by 8, remainder will be 7, already in the set. 3 7s are 21. 21 by 8, remainder will be 5, present in the set. So again, no problem. So let's check for 5. Already checked for 1 and 3. So 5 5s are 25 divided by 8, remainder will be 1. 5 7s are 35 divided by 8, remainder will be 3. So again, no problem. Let's check for 7. So we have already checked 1 3 5. Let's check 7 with 7. So 7 7s are 49 divided by 8, remainder 1, already present in the set. So this set is closed. Yes, sir. This set is closed. Again, because multiplication is associative, multiplication modulo n is associative. So please try to understand. Multiplication modulo n is associative. Okay. Second, sir, what will be the identity with respect to multiplication modulo n? Identity element with respect to multiplication modulo n will be 1. identity with respect to multiplication modulo n is 1. So we can actually see, sir, why is this case? Let's assume let x is less than n. Let x is less than n. With what number we multiply x and divide it by n such that the remainder is x itself? Sir, x is already less than n. So if we divide x itself by n, the remainder will be x itself. So this x multiplication with something should remain x, then only x multiplied by something mod n will produce x. So this will be 1. So if we perform the multiplication of x with 1, that is x multiplication modulo n with 1 is this nothing but x into 1 mod n. So this will remain x. Therefore, identity element with respect to multiplication modulo n is 1. So now identity is present in the side. So sir, yes, it is closed. Identity is present in the set. Associative. You already know multiplication modulo n will be associative for any n. Third, identity equals to 1 belong to set. Now the last thing that we need to check is inverse. We need to look for inverse. So fourth one is inverse. So what do we know? Sir, 1 is the identity element. Therefore, inverse of 1 will be 1. Inverse of 1 will be 1. Now please look at this. 3 3s are 9, divided by 8 will be 1, which is the identity element. So please look at this. 3 multiplication modulo 8 with 3 is equals to 1, which is the identity element. Therefore, inverse of 3 is 3. Inverse of 3 is 3. Similarly, 5 multiplication modulo 8 with 5 is equals to 1. 5 5 are 25, divided by 8, remainder 1 is identity. Therefore, inverse of 5, 5. Similarly, inverse of 7, you can check, inverse of 7 will be 7. But this has just happened in this particular group, that every element is inverse of itself. It is not necessary in a group with respect to multiplication modulo n. So in this particular group, it has just happened that every element is inverse of itself. You can see inverse of 1 is 1, inverse of 3 is 3, inverse of 5 is 5, inverse of 7 is 7. But it is not necessary for every group with respect to multiplication modulo, and we'll take some other example as well so that you will understand that yes, it is not necessary. So inverse is also present. Inverse is also present for every element of the set within the set itself. Therefore, the set 1 3 5 7 form a group with respect to multiplication modulo 8. Okay, let's take one more example. So let n equals to 15. So what are the elements which are less than 15 and co-prime to 15? Sir, 1 is co-prime to 15, 2 is co-prime to 15, 3 is not co-prime to 15, 4 is co-prime to 15, 5 is not co-prime to 15, 6 is not co-prime to 15, 7 is co-prime to 15, 8 is co-prime to 15, 9 is not co-prime to 15, 10 is not co-prime to 15, 11 is co-prime to 15, 12 is not co-prime to 15, 13 is co-prime to 15, and 14 is co-prime to 15. So this set of all these elements, so this set for a group with respect to multiplication modulo 15. So if this is your number n, then set off all the numbers which are less than n and co-prime to n will eventually form a group with respect to multiplication modulo n. Now, sir, so you can check for the closure property, this will be closed. You can check for all the elements, this will remain closed. We already knew it is associative. Sir, identity is present. So these three things are already known. Now let's look for inverse. For inverse, sir, what will be inverse of 1? 1 is the identity element. Therefore, inverse of 1 will be 1. Sir, what will be inverse of 2? With what element we multiply 2 and divided by 15, that the remainder will be 1. Sir, 2 8s are 16. Divided by 15, remainder will be 1. Inverse of 2 will be 8. Therefore, inverse of 8 will be 2. Inverse of 8 will be 2. So what will be inverse of 3? 3 is not present in this side. 4. Sir, 4 4s are 16. So inverse of 4 will be 4 only. Inverse of 4 will be 4 only. What will be inverse of 7? Inverse of 7. So 13 sevens are 91, divide by 15, remainder will be 1. So inverse of 7 will be 13. Therefore, inverse of 13 will be 7. Yes, sir. Now what's 11? So 7. Oh, okay. Inverse of 8 we have already covered. Inverse of 11. So what will be inverse of 11? 11 into 11, 128. Divide by 15. Remainder will be 1. So inverse of 11 will be 11. The inverse of 13 we already know. Inverse of 14 will be 14. Inverse of 14. 14. So inverse exists for every element of the set within the set itself. That is, inverse is present for every element. We also visualize that it is not necessary in a group with respect to multiplication modulo n that every element is inverse of itself. It may be in a group, every element may be inverse of itself, or it may not be the case in a random group with respect to multiplication modulo n. So now we have understood the concept. Now please try to understand that if n is a prime number, note, if p is any prime number, so if p is a prime number, then every integer less than p will be co-prime to p. If p is a prime number, then every integer less than p will be co-prime to p. So if p is any prime number, then set of all integers which are less than p, that is 1, 2, 3, up to p minus 1 will be co-prime to p. Therefore, the set, then the set containing elements 1, 2, 3 up to p minus 1 will form a group. Will form a group with respect to multiplication modulo p. So if p is a prime number, then the set of all elements 1 to p minus 1. If p is a prime number, then the set of all elements 1 to p minus 1 will form a group with respect to multiplication modulo p. So you can actually think of it as a corollary. You can think of it as a corollary of this particular statement, that if n is any positive integer, then the set of all positive integers which are less than n and co-prime to n. So if p is a prime number, then all the positive integers less than p will be co-prime to p. Therefore, 1 to p minus 1, all the set of all positive integers from 1 to p minus 1 will form a group with respect to multiplication modulo p. Okay, so this is with respect to multiplication modulo. And now please try to understand the next concept that we could not complete in the last class. So back to the slide where were. So we have covered this, but we could not complete the concept related to order of an element of the group. So let me complete the concept related to order of an element of the group. Get this. Okay, so talk about concept of order of an element of group G. Talk about order of an element of a group. So, sir, what do we mean by order of an element? Basically, there are two definitions. One is the order of the subgroup generated by an element will be called the order of the element of the group, or otherwise you can understand in a simple way that order of an element A belonging to group G, order of an element A belonging to group G is the least positive integer and least positive integer. That means 0 is not included. 0 is neither positive nor negative. So we'll start checking from 1. So A belonging to G. So the order of element A is the least positive integer n such that if you perform A raised power n, then it should be equals to identity element. Okay. Just 1 minute. A raised power n is nothing but A is not A into A, but the binary operation. So A asterisk A asterisk a n times equals to a raised power n. So don't think of it as a simple multiplication. A raised power n is corresponding to the binary operation with respect to which we are checking for the group. So the order of an element A belonging to set G is the least positive integer n such that A raised power n is equals to identity element. How do we denote the order of element? So order of an element A can be denoted by of A. Let's try to understand this. Try to understand. Yeah. So what do we know? 1 comma minus 1 is a group with respect to multiplication. So this time the operation is multiplication. Respect to multiplication. What do we know? Sir, for what power? Sir, identity element. What is the identity element of this set? Identity is equals to 1. Identity element is 1. So we need a least positive integer n such that a raised power n should return 1. Such that a raised power n should return 1. So positive integer. So 1 raised to the power 1 itself will return 1. Therefore, order of 1 will be 1. Please remember one thing. What, sir? We are actually trying to derive identity element. So for what power of identity element it will return identity element? For what power of identity element it will return identity element? So it is already the identity element. It is already the identity element. Therefore, e raised power 1 itself will be equals to e for all identity elements. Therefore, order of identity element will always be 1. Order of identity element will always be 1. So please note down order of identity element always be 1. Okay. Now for next element, so let's check for minus 1. Sir, minus 1 raised to the power 1 will be minus 1 only, which is not equals to identity element. Minus 1 raised to the power 2 will be equals to 1, which is the identity element. Therefore, what will be the order of minus 1? The order of minus 1 will be 2. Order of minus 1 will be 2. For what power of minus 1 it will produce the identity element? So for power 2, power 2 minus 1 raised power 2 will produce identity element. So now you will say, sir, minus 1 raised power 4 also produces the identity element. Minus 1 raised power 4 also produces the identity element. But we are interested in the least positive integer. We are interested in the least positive integer. Okay, sir. That's one example. Now let's look for two more examples. So what do we know? 1 omega omega square. 1 omega omega square is a group with respect to multiplication. The group multiplication. Identity is 1. Identity. Therefore, order of identity element will be 1 only. Order of identity element will be 1 only. Now let's look for the remaining elements. Sir, let's take omega. Sir, omega raised power 1 will be omega only. Omega raised to the power 2 will be omega square. So this is not equals to identity element. This is not equals to identity element. But omega cube is actually equals to 1, which is the identity element. So for what power of omega we are getting the identity element? So power 3 of omega we are getting the identity element. Therefore, order of omega will be equals to. Similarly, if we look for omega square, sir, omega square raised to the power omega square raised to power 1 will be omega square, which is not the identity element. Omega square raised to power 2 will be omega. So because omega raised to power 4 will be nothing but omega cube into omega. So this will be omega, which is not the identity element. And omega square to the power 6 will be omega cube into omega cube, 1 into 1, which is the identity element. Therefore, order of omega square is also 3. For what power of omega square we get the identity element? So power 3 of omega square we get the identity element. Now let's move to the next example. That should be end, or we'll take one more. We'll conclude the topic. So what do we know? 1 minus 1 iota minus iota form a group with respect to multiplication. Yes, sir, we know. Identity element is still 1. What is the identity element? Identity equals to 1. Therefore, order of identity 1 only. Let's look for other elements. Sir, minus 1 raised power 1 will be minus 1, not the identity element. Minus 1 raised power 2 will be 1, which is the identity element. Therefore, order of minus 1 will be. Let's go back to iota then. So, iota raised power 1 will be iota only. Iota only. Iota square is what, sir? Minus 1. Sir, iota cube will be nothing but iota square into iota, that is minus of iota. Sir, iota raised power 4 will be iota square into iota square, that is minus 1 into 1, that is 1, which is the identity element. Therefore, order of iota. For what power of iota we are getting the identity element? Sir, for power 4 we are getting the identity element. Therefore, order of iota is 4. Similarly, what will be order of minus iota? Sir, minus of iota raised power 1 will be minus of iota only. Minus of iota square will be plus of iota square, which is minus 1. Minus of iota cube will be nothing but minus of iota cube. Iota cube is minus iota, so minus of iota cube will be plus of iota. Similarly, minus of iota raised power 4 will be nothing but 1, which is the identity element. Therefore, order of minus iota is also 4. Order of minus iota is also 4. Last example to conclude the concept. Okay. So we just checked that 1357, 1357, the group with respect to multiplication modulo 8. So why am I taking this example? Because in all previous example you could not figure out that what do we mean by a raised power n. So we are simply taking simple multiplication, therefore a raised power n will be nothing but a into a n times. Now if the operation is multiplication modulo 8, then how do we calculate the 1 square, 2 square, 3 square, etc. So let's check for this. Sir, what is the identity element? Sir, identity is equals to 1. So whenever you have the identity element, order of that identity element will always be 1. You don't need to perform any operation. You don't need to perform the operation of identity element with any thing to generate the identity element. Okay. So now that's one thing. Now let's look for 3. So 3 raised power 1 will be nothing but 3. But if I say 3 square, then what do we mean by 3 square? What do we mean by 3 square? So 3 square is nothing but 3 operation is a multiplication modulo 8. So 3 operation, so that's that is perform the operation on 2 A's. So 3 multiplication modulo 8 with 3. So what is the result? So 3 3 is 9 divided by 8, remainder 1, which is the identity element. So for what power of 3 we are getting the identity element? So for power 2 of 3 we are getting the identity element. Therefore order of 3 will be 2. Order of 3 will be 2. Similarly, 5 raised power 1 will be 5 only. 5 square is actually nothing but 5. Multiplication modulo 8 with 5. 5 5s are 25 divided by 8, remainder 1, which is the identity element. Therefore, order of 5 is also 2. Order of 5 is 2. What else? 7, 1 raised power 1 will be 7. 7 square will be nothing but 7 multiplication modulo 8 with 7. 7 sevens are 49 divided by 8. Remainder 1. That is the identity element. Therefore, order of 7 is also. Okay, one last example. One last example. Sir, we know that 0, 1, 2, 3, 4 is a group. The group with respect to what? Addition modulo 5 is a group with respect to addition modulo 5. In this case, what is the identity element? Sir, identity with respect to addition modulo n is nothing but 0. So identity is equals to 0. Therefore, order of 0 is equals to 1. The order of 0, not O of O. Order of 0 equals to 1. So now let's talk about 1. Sir, 1 raised to the power 1 is 1. 1 square is nothing but 1 addition modulo 5 with 1. So 1 plus 1, 1 plus 1 divided by 5, that is 2 divided by 5, remainder will be 2, which is not. So this 1 is not the identity element, this is also not the identity element, because identity element is 0. Identity element is 0. Now please look at this. Sir, what is 1 cube? 1 cube can be written as 1 addition modulo 5 with 1 addition modulo 5 with 1. Now we know the operation is associative. We know the operation is associative. Therefore, we can perform the operation in any order. So we can first perform the operation 1 addition modulo 5 with 1, and then the result can be uh, evaluated with 1. So this is actually nothing. Can we write it? 1 addition modulo 5 with 1 is nothing but 1 square addition modulo 5 with 1. What is the value of 1 square? So 1 square is 2. So basically we are writing 2 addition modulo 5 with 1, and 2 addition modulo 5 is 1 is nothing but 3. So this is not the identity element. Similarly, sir, if we look for 1 raised power 4, for 1 raised power 4. So 1 raised power 4 can actually be written as 1 raised power 3 addition modulo 4 with, sorry, addition modulo 5, not 4. Addition modulo 5 with 1. So 1 raised power 3 is nothing but 3. So it's actually nothing but 3 addition modulo 5 with 1. 3 plus 1, 4 divided by 5. Remainder 4, which is not the identity element. So what is 1 raised power 5? So 1 raised power 5 will be what? 1 raised power 5 will be 1 raised to the power 4 addition modulo 5 with 1, which is equals to, yeah, sorry, this will be the operation 1. This is 4 addition modulo 5 with 1, which is the 4 plus 1, 5 divided by 5, remainder 0, which is the identity element. So for what power of 1 we get the identity element? So we get identity element for power 5 of element 1. Therefore, order of 1 is equals to 5. I have given you an idea. So I'm simply writing the order for other elements. You can simply cross check. So what will be the order of 1? Okay, so order of 2 will be order of 2 will be order of 2 order of 2 order of 2 will also be plus 4 be 1, right? So yeah, so order of 2 is also equals to 5, order of 3 will also be equals to 5, and order of 4 will also be equals to 5. You can cross check that. You can cross check the order of every element except the identity element is 5 in this set. There is a rule because of which this is happening. But anyway, so we have checked that how do we evaluate the order of an element. Now please try to analyze certain things. Sir, in this particular example, what is the order of the group? Sir, in this first example, order of group is what? So there are two elements in the set. In this example, what is the order of the group? So order of group is 3 because there are 3 elements in the set. What is the order of this group? So order of group is 4 because there are 4 elements in this set. What is the order of the group? So order of the group is 4 because there are 4 elements in this set. What is the order of the group? So order of group is equals to 5 because there are 5 elements in this set. Now, what do we visualize? That the order of element, the order of the group is 2 and the order of element is 1 or 2. That means the order of element 1 divides the order of the group. Order of element -1, which is 2, also divides the order of the group. Apart from that, here order of the group is 3. So order of element 1 is 1, which divides 3. Order of omega and omega square is 3, which also divides 3. So here order of 1 is 1, which divides order of group, that is 4. Order of -1 is 2, 2 also divides 4. Order of iota is 4, 4 also divides 4. Order of minus iota is also 4, 4 divides 4. So order of every element of the group, order of every element of the group will divide the order of the group. So that's note which you can away. So in a finite group, order of every element is less than or equal to, order of every element is less than or equals to order of the group, and order of an element of the group divides the order of the group. So it will never happen that order of an element will be more than the order of the group. It will never happen that the order of an element of the group will be more than the order of the group. And apart from that, order of an element of the group divides the order of the group. So if the order of group is whatever n, then order of every element will be a divisor of n. Order of every element of that group will be a divisor of n. Now, let's go back and try to understand. Sir, what do we know? Here, omega is the order of omega is same as order of omega square. Omega and omega square are inverse of each other. Here also, iota and minus iota are inverse of each other. So order of iota is same as order of minus iota. In this case, inverse of 3 is 3. So that's a different thing. That's not important. So order of 1 and order of 4 will be same, because 1 is inverse of 4. We can actually see order of 1 is same as order of 4. 2 and 3 are inverse of each other. 2 plus 3, 5 divided by 5, remainder 0, identity. So 2 and 3, 5 are inverse of each other. Therefore, order of 2 and 3 will also be 5. Apart from that, please try to understand, order of this group is a prime number. Order of this group is a prime number. So what value can divide a prime number? Sir, either one will divide a prime number, or the prime number itself will divide a prime number. But there cannot be any other element in the set apart from the identity element whose order is 1. So, order of an element can be 1 only if that element is the identity element. So, please note down some more points if you want. What is it? Order of an element can be 1 only if element is the identity element. If the element is the identity element. Apart from this, what did I say? Omega and omega square are inverse of each other. Therefore, order of omega will be same as order of omega. Order of omega will be same as order of inverse of omega, which is omega square. Iota and minus iota are inverse of each other. Therefore, order of iota will be same as order of inverse of iota, that is minus iota, etc. So, order of an element A is same as the order of its inverse. Order of an element A is the same as the order of its inverse. So, these are some properties. Now, let's move to the next topic. This topic, subgroup of a group. So, how do we define the concept of subgroup? So, this is topic which we were supposed to cover in the today's session, but because of some dependency, we'll cover only subgroup, and we'll start the discussion of cyclic group in the next. In today's class, we'll only discuss the concept of subgroup, and we'll complete the topic of cyclic group in the tomorrow's. Let's understand the of subgroup. The subgroup, we already know it must be related to the concept of subset. Okay, so let's assume let G asterisk be a group. So we know that elements of set G are satisfying 4 properties with respect to binary operation asterisk. What are those properties? Closure, associative, identity, and inverse. Then only this G can be a group. So let this G asterisk be a group. If I take a subset H of set G, then will it form a group with respect to binary operation S? We don't know. So the subset H of G is called a subgroup of group G is called a subgroup of group G if and only if the set H with respect to binary operation asterisk satisfies the property of a group. If and only if the set H with respect to binary operation asterisk satisfies the property of a group. Clear? Now please try to understand. Please try to understand. If I take any group, let 1 minus 1 iota minus iota is a group with respect to multiplication. Respect to multiplication. Okay. Now what? Now the idea is that if I take the subset that contains only the identity element, if I take this is a set, in this set, if it is a group, we know that identity element is guaranteed to be present in this set. So if I take a subset in which only the identity element with respect to binary operation is included, then it will always form a group with respect to binary operation, and this will eventually become a subgroup of this group, because if a subset satisfies the property of a group with respect to same binary operation, then that will be called a subgroup of the original group. Now, so this one is a subgroup of above group with respect to multiplication, obviously, with respect to same operation we are talking about. Okay. Now, another property that we know is that every set is a subset of itself. Every set is a subset of itself. So, this is what, sir? Subset 1. Another thing is, we know every set is a subset of itself. Subset 1 minus 1 iota minus iota is also a subgroup of above group with respect to multiplication. Sir, by looking at this statement, you will say, sir, this is the same group. Why are you calling it a subgroup? Because every set is a subset of itself. Because of that reason, every group will be subgroup of itself. Every group will be subgroup of itself. Now, sir, from this set, if we take a subset in which only the identity element is present, then it is guaranteed to be a subgroup of the given group. If I take all the elements of the set, then also it is guaranteed to be a subgroup of the group, because previous set itself is satisfying all four properties of a group with respect to binary operation. Therefore, this subset that contains all the elements will also satisfy the properties of group with respect to same binary operation. But if I take any other subset, is it necessary that the subset will satisfy the property of a group? Let's check. Let's check. So what? So subset, if I take subset 1 comma minus 1, if I take subset 1 comma minus 1, so please tell me this subset 1 comma minus 1 satisfies all the properties of our group with respect to multiplication or not? Yes, sir. Subset 1 comma minus 1 is also a subgroup of above group. Now, last question that will arise in your mind is that, sir, does it mean that any subset of the given set will be a group? Does it mean that any subset of the given set will be a group with respect to binary operation? No, sir, it is not necessary. So let's check. Subset, if I take subset 1 comma iota, if I take subset 1 comma iota, is it a group? Is it a group with respect to multiplication? No, sir. iota into iota will be iota square, which will be -1, which is not present in the set. Therefore, it is not closed. Therefore, it is not closed. Subset 1 comma -1 is not closed. Is not closed with respect to multiplication. With respect to multiplication, therefore, 1 comma iota is not a subgroup. Is not a subgroup of above group. Is not a subgroup of above group. So, sir, what did we learn? Sir, we learned two different type of things. What, sir? For any group G, the subset containing only the identity element and the subset containing all the elements of that group are guaranteed to be the subgroup of the given group. So, and these two are trivial things. I mean, we are not providing any much useful information using this two concept. Therefore, these two subgroups are called a trivial subgroup. You are not giving very important information. You are just telling me that every group is a subgroup of itself. We know that because every set is a subset of itself. Similarly, if you have any set that contains only the identity element with respect to binary operation, then that set will also satisfy all four properties of a group. Therefore, it is also a trivial thing to say. So, what can we say? Sir, let G asterisk be a group, then trivial subgroups of G are the set containing the identity element E and the set G itself. The set containing the identity element E and set G itself. So, where E is the identity element. You already know this, but so for any group, it is guaranteed that there will be two subgroups of that group. One is the group itself, another is a subset that contains only the identity element with respect to binary operation. So for any group G itself and the set containing the identity element are called trivial subgroups of group G. If you have any other subgroup of group G, then it will be called a proper subgroup of group G. So any subgroup of G which is not trivial. So apart from these two, so these are the only two trivial subgroups. So any subgroup which is not trivial is called proper subgroup of group G. Is called proper subgroup of group G. So in the previous slide, 1 comma -1 is a proper subgroup of group 1 minus 1 iota minus iota with respect to multiplication. Obviously, and these two are what trivial subgroup. Trivial subgroup and proper subgroup. Clear? So these are some important things related to concept of subgroup. Let's try to understand. Yes. Sir, some more examples. So let 1, 3. We have already seen that this 1, 3, 5, 7 is a group. With respect to multiplication modulo 8. Is a group with respect to multiplication modulo 8. Now, please try to 1 is a trivial subgroup 1 is a trivial. If I take a subset which contains only the identity element, 1 is a trivial subgroup of above group with respect to multiplication group itself. I don't need to. This group itself will also be a trivial subgroup of the above group. But apart from that, please look for, so 1 and 3. Please tell me 1 comma 3 is a subgroup of the above group or not. So the idea is, sir, the subset should follow all four properties of the group with respect to same binary operation. Now my question is, 1 comma 3 is closed with respect to binary operation multiplication modulo 8 or not? So sir, 1 into 1 divided by 8, remainder 1 identity. 1 into 3, 3 divided by 8, remainder 3 already in the set. 3 into 1, 3 divided by 8, remainder 3 already in the set. 3 3s are 9 divided by 8, remainder 1, it is in the set. So it is closed. Sir, operation multiplication is already associative. Now, identity element 1 is present in the set. Inverse of 1 is 1, inverse of 3 is 3. So, inverse is also present for every element of the set within the set. So, this 1 comma 3 is a proper subgroup of above group with respect to multiplication modulo 8. Similarly, 1 comma 5 is also a proper subgroup. You can check. So it is closed, it is associative, identity is present, inverse of 1 is 1, inverse of 5 is 5. So 1, 7 is also a proper subgroup of the above group with respect to multiplication modulo 8. Okay. Okay. Now please try to understand, when I was providing the definition of the order of an element. So where is order of an element? The order of an element A belonging to G, the least positive integer n, such that A raised power n equals to identity element. So the idea is, before A produces this identity element, the elements which A has already generated up to this element E will form a subgroup of the group G with respect to same binary operation. Let's try to understand. So what is happening? What is happening? So 3 raised power 1 will be 3, 3 raised power 2 will be 1. So before producing the identity element, 3 has generated two elements, 3 and 1. So 5 raised power 1 will be 5, 5 raised to power 2 will be 1. So before generating the identity element, 5 has generated two elements, 5 and 1. Therefore, it is a subgroup of the above group. Sir, what is the order of the 5? Sir, order of the 5 is 2. Why? Because it generates identity element at 5 raised power 2. Therefore, it will generate two different elements. It will generate two different elements before it generates the identity element. Now the concept is, sir, the order of the subgroup will be same as the order of the element which is generating that subgroup. So basically 5 is generating this subgroup because 5 raised power 1 will be 5, 5 raised power 2 will be 1. So all the elements of this subgroup can be generated by 5. Therefore, order of this subgroup will be same as the order of the element which is generating this subgroup. Now, order of an element will eventually divide the order of the group. Order of an element will divide the order of the group. Therefore, the most important property with respect to subgroup concept is that order of the subgroup will definitely divide the order of the group. But important thing is that, sir, the order of this subset is 2. Therefore, the order of this subgroup is 2 and the order of group is 4. So, order of subgroup divides the order of the group. But if I take any subset of order 2, then is it necessary that that subset will be a subgroup of the given group? No, sir. If I take subset 3, 5, then the size of this set is 2. It divides the order of the set, Now order of the group, that is 4. So size of this subset divides the size of this set. But it does not mean that this subset will create a subgroup of the group. So it's one way only, that if given set is a subgroup of the original group, then the size of the subset will definitely divide the size of the set. But if I take any random subset of size such that the size of the subset divides the size of the set, then it is not necessary for that subset to form a subgroup of the given group. So it's only one way implication, it's not two way. Okay, so please don't get confused. If I am saying that order of a subgroup divides the order of the group, then it means that if the given set is a subgroup of the group, then the size of the subset will divide the size of the set. But any subset of size such that that size divides the order of the set need not be the subgroup of the original group. So anyway, so that's just one property that we'll talk about. So it's just an extra side, properties with respect to subgroup. So the very first property is let comma asterisk is a group and h comma asterisk is the any subgroup of group G. Then order of H divides order of what does it mean? That is order of subgroup of group G divides order of group G. So if you have any subgroup, then the order of subgroup will divide the order of the group. Now, another important property, what? Let G comma asterisk is a group and is any H is any non-empty subset of group G. H is any non-empty subset of G. Then H comma asterisk is a subgroup of G H comma asterisk is a subgroup of G comma asterisk if and only if A asterisk B plus belongs to set H for all A and B belonging to set H. So this is one important property, that if G is any set and if G is any group and if you take any subset H of G, which is a non-empty subset, then H with respect to binary operation asterisk is guaranteed to be a subgroup of group G if this property is satisfied. What property? That for all the elements A and B belonging to set H, if A asterisk B inverse also belongs to set H, then this set H will follow all four properties of group with respect to binary operation asterisk. That is, it will follow the identity, it will have the identity element, it will have the inverse of every element in the set, it will also be closed with respect to binary operation asterisk. Apart from that, sir, only thing that we don't know is whether asterisk is associative or not. So G is already a group with respect to binary operation asterisk. So if asterisk is associative with respect to elements of set G, then asterisk will be associative with respect to elements of set H also. So three properties, that is identity, inverse and closure property, can be derived for the elements of set H by using this particular definition, that for all A and B belonging to set H, if A asterisk B inverse also belongs to set H, then identity element with respect to binary operation asterisk will be present in the set, and inverse of every element will also be present in the set, and for all A comma B belonging to set H, A asterisk B is also present in the set H. It can also be concluded by a single statement. Okay, so this is again the most important property with respect to subgroup concept. What else? Sir, what else? What else? Yeah. So next property is that, okay, let G comma asterisk is a group and H1 comma asterisk and S2 comma asterisk are two subgroups of group G, of group G comma asterisk. So statement 1, H1 union H2 is a subgroup of group G. H1 union H2 is a subgroup of group G if and only if, A, H1 is a subset of H2, if and only if H1 is a subset of H2, or H2 is a subset of H1. That is, if you take the union of H1 and H2, it should either be H1 or it should either be H2. If it is not satisfied, then the union of H1 and H2 will not satisfy the closure property with respect to binary operation asterisk. Therefore, if H1 and H2 are two subgroups of group G, then union of those two subgroups can be a subgroup of the group G if and only if one set is contained in another set. So either H1 is contained in H2 or H2 is contained in H1. So if H1 is contained in H2, then H1 union H2 will be equals to H2. And if H2 is contained in H1, then H1 union H2 will be equals to H1. So H2 is already a subgroup, therefore H1 union H2 is actually H2. Therefore H2 will already, H1 union H2 will also be a subgroup of the given group. Now H2 union H1 will be H1, and we know H1 is already a subgroup. Therefore H1 union H2 will also be a subgroup. But this is with respect to intersection only. This is with respect to, this is with respect to union only. What will be the case with respect to intersection? So if H1 and H2 are two subgroups of group G, then G1, then H1 intersection H2 will always be a subgroup of group G. So first this, second, H1 intersection H2 is always a subgroup of group, is always a subgroup of group G. We can simply prove this property, but as of now we don't need to go into that much detail. So yeah, so these are three important, but there may be some other properties with subgroup. So the very first important property is that order of subgroup will divide the order of the group. If H is any non-empty subset of set G, then H with respect to binary operation asterisk will form a group if and only if for all A and B belonging to that subset H, A asterisk B inverse should also belong to set H. So if A asterisk B inverse belong to set H for all A and B belonging to set H, then H with respect to binary operation asterisk will satisfy three properties: identity, inverse, and closure property. Asterisk is already associative, therefore it will form a group, and H will be a subgroup of the. Now third one is with respect to union and intersection, that is if H1 and H2 are two subgroups, then H1 union H2 may or may not be a subgroup of group G. It will be a subgroup of group G if H1 is subset of H2 or H2 is of H1. But H1 intersection H2 always a subgroup of G. Clear? So that will be all for this particular session. So there are three last class. I am concluding those two lectures from yesterday and a single lecture because we could not do this summary part in the last class. So we have understood the concept of finite group. We know the concept of addition modulo M operation. Know the concept of multiplication modulo M operation. We know that how do we determine the order of an element of a finite group. Order of an element of a finite group is nothing but the least positive integer n such that a raised power n results in the identity element. Now please remember, identity element, with respect to identity element, order of identity element will always be equals to. Apart from that, if the order of an element is equals to 2, order of an element is equals to 2, then that element will be inverse of itself. Then that element will be inverse of itself. Please try to understand. If I am saying order of an element A is equals to 2, what does it mean? That is A is square equals to identity element. What does it mean? A asterisk A is equals to identity element. So for two elements, if the binary operation of those two elements produces the identity element, then they are inverse of each other. So if order of A is equals to 2, then inverse of A will be A. So if order of element A is equals to 2, for any element, if order is equals to 2, then that element will be inverse of itself. Clear? Okay, we have also understood the concept of subgroup. A subset such that the element of that subset satisfy all the properties of a group with respect to same binary operation asterisk will be called a subgroup, and the properties that order of subgroup divides the order of the group. Yes, and the other two. One is with respect to a union and intersection. Another respect to that for all a comma b belonging to set H, if a strict was also belong to set H, then H will be a subgroup of group G. That will be all. Thank you very much for joining the session. In the tomorrow session, we'll discuss the concept of cyclic group. There is one more property related to concept of subgroup. That's subgroup of a cyclic group is also a cyclic group. The generator of the cyclic subgroup need not be same as the generator of the original group, but the idea is that is related with the definition of cyclic group. Therefore, I'll include that particular property in the next session along with some more properties of the group. So tomorrow's session will be very important because there are some specific properties of the group from which the questions can be directly asked. Now, if you go and check the previous year question papers, then last 5 years they have asked a question related to this concept thrice in the GATE exam. So very frequently they ask a question from this particular concept. This is known as Lagrange's theorem. This is known as Lagrange's theorem, that you don't need to go into the proof of that particular statement. You only need to understand that if a question comes, then you must know that order of a subgroup guaranteed to divide the order of the. Okay, so that will be all. Thank you very much. See you tomorrow with the concept of cyclic groups. Till then, take care, keep learning. Have a nice day.